Now we're going to use the vector data model as a way to illustrate or represent or visualize the surface of Mount Etna. Over on the left-hand side, this is the DEM that we just produced from the Raster data model video. And over here on the right is what we call an isoline map. And so it's the most common way to show a change in the vector data model is the isoline map. In this case, we're going to call them contour lines because we're referring to elevation. So how do these suckers form? How do we create a contour line? There's some certain rules that I'll go through as far as how to do this, but it's very simple. Isolines are just essentially lines that connect points of equal value. So in this particular map, we have a bunch of 40s. So think of this as maybe being temperature. So often you'll see weather stations that record different temperatures, and then you'll see a map produced of like reds in certain areas that show warm areas, and blues are cold areas, and green somewhere in between. And all that is based off of individual points, weather stations, in which they then create or interpolate from that isoline or isotherm maps. And so this is just essentially a way to show this continue this particular line all the way. And so now I've created an isoline map. And so each of these individual lines, notice they do not cross each other. They either go to the edge of the country or they form a circle. So they don't break apart either. So once again, all points along the same line. So if I'm going to the right in this case, everything's going to be lower than 40. If I go to the left, everything's going to be greater than 40. And so you can see as we go through this, you're going to see steeper slopes or when the lines are closer together. And so what that means here is the temperature here, 70 degrees. Just over here, 40 degrees. Huge swing in temperature, huge variation in temperature. So when we see that on the surface, lines closer together on the surface is going to indicate steeper slopes. Whereas flatter surfaces are when we see the lines more spread apart. And so think of that here, less change, less variation in temperature as those isotherms, as these isolines become farther apart. Here what I've done is I zoomed in to the top of Mount Etna, the summit, so you can see the isolines. Once again, all the lines either go to the edge, or where we don't see them anymore, or they form a circle. They form their own circles. We don't see, if you zoomed in close enough, you don't see any lines crossing each other, breaking off. They all form concentric rings. And so as in this case, as we go up the slope, we're going up in elevation, we can see steeper slope right through here, and then it starts to flatten out because the lines get a little farther apart. Of course, the top of the mountain, in this case, is shown as being quite flat, whereas you got from there, goes down considerably. And this is common because of what we see here is a volcano, which is blown off its top. So that's why we see a relatively flat top here. In this case, the map has a contour interval of 25, and all that means is that's just the difference in terms of the value of this line to the next line. So let's just say hypothetically this particular line is 2,000 meters. All that's saying is the next one, because I know we're going up the slope as I go towards the top of the mountain. The next one, 2025, 2050, 2075, and so on. Now what I'm going to do is I'm going to zoom into a particular area of this DEM and compare it to the use of an isoline map or a contour line. So we can see, of course, we got raster, so we'll continue. So this is the DEM. Now, in case of this using the same exact area, all I did was to say, okay, GIS, turn this area into a contour line map. And so essentially that's what it did here. And so we can see the values here. And so I guess a positive or an advantage, let's say, of the isoline or the contour line map is that this particular data model, the vector data model, is that we can actually see the values shown on the map. We actually know exactly what the elevation is there just by looking at it. We don't have to get out our computer or get out our app and then point on it and see, okay, the pixel value is. No, we don't have to do that. It's shown essentially on here. But yeah, there is some disadvantages of there's some gaps here. I mean, it doesn't really show every single part of the landscape. And one way we can do this still in the vector data model, though, is by turning those raster grids, those individual squares, from individual squares, and just put a circle or a dot right in the middle of those individual cells. And that's what I did here. And so this is using what they call the raster to point feature. And this is a huge amount of data, and so it's hard to tell. But if you can see clearly, we got some brown dots up there, and yellow here, green. So once again, those represent different values, and so we have our X and the Y, so essentially the center of each of these raster grid cells, combined with the Z value, which is the elevation, and is then showed in different colors. So this is the vector data model in which it uses points, but notice how they are regularly spaced. They're all right next to each other. And so they're very evenly spaced, which is different than the next model I'm going to talk about in the next video. One of the things is, you've already done this already in terms of using the vector data model in terms of creating elevation difference with the building heights from the exercise 2 project that we did earlier in the semester. So it's the same idea, but what we did was just manually created the 3D by creating the attribute data that then the vector data model then created this particular section in the third dimension.